So we define representation of graphs in computer engineering. It's usually a adjacency list, but in math it is better to represent a graph as a matrix. Usually it's an adjacency matrix. It can also be an incidence matrix. And then we defined the problem of graph isomorphism. Right? What is the key structure inside a graph which you want to talk about without getting into the specifics of the labels of the vertices? Any questions till now? So, yeah, you can show that graphs are isomorphic if and only if their complements are isomorphic. Right? This follows from the definition, because the edges have to be preserved and the non-edges have to be preserved. So it doesn't matter whether you look at G or its complement. So you can use that to give a formal proof. Yeah, other question you can do is classify all the graphs on 4 vertices and let's say at most 4 edges, as we drew here, H1 to H3. But there are more possibilities. You may have 2 edges in different ways. For example, you may have parallel edges instead of the incident on a vertex. Or you may have 3 edges or you may have 4 edges, right? So you can look at all those cases and classify. So construct all non-isomorphic graphs on vertices 4 and edges, number of edges, at most 4. Okay, you can do this as an exercise. Simply by hand you can draw all these graphs and see which one of them are isomorphic, so you can remove that. What remains are non-isomorphic, such graphs. Another question is, can you construct 2 graphs which have the same degree sequence but they are non-isomorphic? Sorry? 2 triangles, right? Non-isomorphic graphs but same degree sequence. Right, so do they exist? So as suggested, you look at the following picture. Okay, I draw this as a star, but actually the vertices are only the outer 3 plus 3. Okay, so this is one graph, graph number 1, and the other graph is same vertices but now I can draw it as a hexagon. Right, so the vertices are 1, 2, 3, 4, 5, 6 and same here. But you can see that these 2 are not isomorphic. Why? Why is there no bijection that respects edges? Can you give a proof? Right, so H is actually C6. Right, if G was isomorphic to H, then you should see a C6 in G also. But there is no C6. Is that clear? So this is This is C3 disjoint union C3, while this is C6. So you can formally prove that these two are non-isomorphic. But still, the confusing thing is that if you look at the degree sequence, for C3 and C3 it's 2, both are cycles, and for C6 also it is 2. Everything is 2, right? So by looking at the, and obviously the number of vertices is 6 in both the cases. So exactly same degree sequence, but very different structures. And of course, there are many ways to embed, right? So instead of star, you could also have drawn just this. That's the same graph. Right, so the same graph, you can label it differently, you can also orient it differently, but we say that it's the same graph. Formally we say that they are all isomorphic. Is this clear? Okay, so what happens to the adjacency matrix representation of a graph? How does that change under isomorphism? So adjacency matrix AG or AG prime so for example here it can be 1, 2, 3, 4, 5, 6. Okay, so that's very different from G. So adjacency matrix of these graphs, they don't look the same, but that does not mean at all that the graphs are not the same. Right? So isomorphism is a deeper property than the looks of it. So it depends, the matrix depends on the order of the vertices. So the question at the level of matrix is there a way to reorder the vertices? Same way in the row and the column. Okay, you permute the row and in the same way you permute the column, and then the matrices should become equal. So does there exist a permutation pi on row and column that makes AG the same as AG prime? Okay, so you have to ask this question. So obviously in the orange case, there is a permutation. You can just replace 1, 2, 3 of G prime with let's say 1, 3, 5, and 4, 5, 6 of G prime with the rest, 2, 4, 6 and so on. So if you correctly define the permutation, then on say G, if you correctly define the permutation of that sends G to G prime, then the matrix AG will get transformed to AG prime. They will become equal. Okay, so this permutation is basically the bijection on the vertices that respects edges. But finding this, so how will you find this? How will you find pi? How easy is that? If vertices are n, then the number of permutations is n factorial, right? So already for again 100 vertices, this is 100 factorial search space. So this is impossible to solve in practice. Okay, and no good algorithms were known. Only few years ago, something which is better than brute force was discovered. So there is Babai's algorithm, you can read on that. For graph isomorphism. Other than this, the algorithms were usually just brute force. Basically try to learn parts of this permutation and then patch them up. But they were not genuinely fast or generally fast. They were all like this n factorial. Yeah, so this isomorphism defines actually a relation on the graphs. So graphs GT will be related if G and T are isomorphic. Okay, so in the space of all graphs, we can define relations. We can define the relation that a pair of graphs is they are related if a pair of graph is in the relation if G is isomorphic to T. And will this relation be an equivalence relation? Right, because it's reflexive, symmetric, and it is also transitive. So hence there will be, you can decompose the set of graphs into classes. Right? Each class basically contains all possible ways in which you can draw a graph. So they are all essentially the same. So this relation isomorphism is an equivalence relation. Each class contains the isomorphic graphs. So you can take any graph in a class and then you know the class because everything else looks the same. Like we did in this example, both G and G prime, they are in the same class. They look, they don't really look the same, but there is an orientation when they will look the same. And same thing with here with H2, same class, H3, same class. So that class is, I'm calling it HI. Okay. So similarly, you can construct examples of non-isomorphic bipartite graphs. On M plus N vertices. So this example will be left hand, you have M vertices, right hand side is N vertices. Give me an example where two graphs which are non-isomorphic and bipartite. Can you do it on 2 and 2? With the same amount of edges? What about this? These, are they in different class or same class? Same class, right? So, is there an example with 2 edges and 2 plus 2 vertices? How about this? Right? So, even this is a simple case you had to think, but you can see that the first two are isomorphic, the third is in a different class. This is how we are seeing it. Right? And how do you show that this third graph is non-isomorphic to the previous two? Yeah, they differ just in degree sequence. 2, 0, while the others were 1, 1. Okay. This example actually you have already seen. 2 D-regular graphs, non-isomorphic. What's the example? We already saw this, right? This G and H, both of them are 2 regular, but they are non-isomorphic. Right? So, just being regular doesn't mean anything. There are a lot of such graphs that are non-isomorphic. Okay. Any questions? So, we move to a very important concept, both in math and probably more in computer science, which is called connectivity. So, for connectivity, we will define first many other terms to do with simulating a walk on a graph. Right? Graph is an invitation to walk because you have these vertices and you have edges which are like roads. So, you can start walking from any vertex and reach other vertices. So, the way you can walk is, first is definition of a walk. So, walk of length k is a sequence of vertices x0, x1, xk, where, what do you want in the sequence of vertices? X0 to x1 there is an edge, right, and x1 to x2 there should be an edge. So, where each of these xi plus 1 should be an edge in the graph for all I, 0 to k minus 1. So, it's a, I mean, you can see this as a physical walk, but mathematically what you can say is it's a, if you have a k plus 1 tuple of vertices where every consecutive vertex you can reach by an edge, there is an edge, then we say that the k plus 1 tuple is a walk, right? That's what we are formally saying here. So, in particular in a walk it is allowed to repeat vertices and also repeat edges, right? All kinds of repetition is allowed. You can come back on the same edge, on the same vertex. or you may take different vertices, you may not repeat edges, whatever, everything is allowed. And K is the length, K is called the length. Which is equal to the number of edges, right? And we are not saying distinct edges again, edges may repeat. So we can further now restrict it. We may say that either the vertices don't repeat or the edges don't repeat, and that will give you different terms. So if all the vertices are distinct, then the walk is called what is the term? Yeah, if the vertices are distinct, then you call it a path. Some texts also call it simple path. Some texts may call walk a path and then this path a simple path, but we will go with the definition that is written here. And the third thing is so if x0 is xk, okay, if you come back from the place you started, then it is called, then it's a cycle, and we want k to be at least 2. So if x0 is xk and length is at least 2, then it is a cycle. Yeah, so we at least x0, x1, x0, x1 and then again x1. Or maybe if this is confusing, let's replace k here by length. So basically we need 2 edges minimum. Because otherwise what you may be saying is a self loop. Okay, so we don't consider that a cycle, we need you to take an edge from x0 to x1 and x1 to x2 and then come back. That kind of a thing we need. But anyways, the idea is clear. Cycle means that your origin, start vertex and destination. Source and destination should be the same. Then the path becomes a cycle. Yeah, let me say that properly here. Then the path is called a cycle. So immediately you can see that walk is a more relaxed form of a path, and path is a more relaxed form of a cycle. Yes? Sorry? Path and a cycle. Walk and a path. Okay. So give me a walk that is not a path. So 2, and then you may go to 3. Actually, let me not draw it, just say it. So if you go from 1 to 2, take the edge 1 to 2, take the edge 2 to 3, and then it's an undirected graph, so you can again take the edge 3 to 2, go back, and then you can go to 4, say, by an edge. Right? It's a walk, but it's not a path, because the vertices 2 are repeating. Yeah, actually I should have said except in the definition. That's a good point. Except maybe x0, xk. Is that fine? So in a path you are allowed to come back, but in the middle you are not supposed to repeat. You are not allowed to repeat. And cycles are where this repetition happens. Okay. So this is a walk, but not a path. Yeah, so some of these boundary cases can be confusing, but at least first you remember the idea, which is cycle you come back where you started, path is you don't come back usually, and walk is where you can do anything you want. So yeah, so these 3 things I have said, they are all different, strict, so maybe quickly go through this example. So there is the graph with vertices on 1 to 4, edges are 1, 2, maybe it's better to draw this. So 1 to 2, 2 to 3, don't want directions. 4, 1, and 4, 2. Okay, that's the graph. 5 edges. So the sequence 1, 2, 3, 4, 1. This is a walk. Well, everything is a walk because the edges are consecutive. Is this a path? It's a path. Is it a cycle? Yeah. Then 1, 2, 4, 3, 2, 1. So 1, 2 to 4, 3, 2, 1. Yeah, that you can see that it's a walk. What else is this? Is this a path? Not a path. Not path, and hence it's also not a cycle. And finally 1, 2, 3, 4. This is a walk. What else is this? This is also a path and cycle. It's not. Right, so you can see that these three things are all different and these terms are needed. Right, there is a walk which is not a path, there is a walk path that is not a cycle. Okay, so let's prove the first property now, first connection between these three things. So a walk between u comma v implies that there is a path between u comma v. Can you show this? If in a graph you see a walk, then there is also a path between the same source and destination pair. So consider some walk u is x0, then you go to x1 dot dot xk, which is v, and assume that this is of least length. Okay, so now how do you show that there is a path? So what stops this walk from being a path? Something is repeating, right? So what do you do if something repeats? Exactly. So if there is some repetition, then you truncate that part and you have a smaller walk. So if the vertices are distinct, then you are anyways done. So something should be repeating. So let's look at that case. Let V occur twice. Let me call this walk P. Let V occur twice in the walk P. So what you have to do is delete that everything between V and V. So delete the section from V to V. Right, so when you, if you are already at V and after a long walk you return back to V, then just skip that part, that sub walk you delete, and you do what you are supposed to do when you reached V in the future. Right, so from that V, if you were going to W, then already in the past from V you should have moved to W. So now you will still have a walk and it's smaller. It goes from x0 to xk. So we get a walk from x0 to xk of smaller length. Right, so that is the proof by contradiction. So that's a contradiction, which means that P is already a path to begin with, right? Is this clear? Any questions? So all the proof is doing is that if there is a walk, then it just picks the shortest walk. Okay, the shortest walk is a path. That's all we did. Okay, second. So walk with the start and the end vertices the same, and no two consecutive edges the same. Implies that there is a cycle. So is there any reason why the statement is so long? Why can't we just say that if there is a walk from x0 to xk, both of them equal, then there is a cycle? Yeah, so there will be a problem if you were using consecutive edges same. So you may do silly things like here you look at 1, 2, 1, right? So this is a graph which is clearly cycle free, but you will not see this in a walk. So if you look at 1, 2, 1, then walk is so generally defined that this is also a walk, but it doesn't mean that you have a cycle. So what the problem here is that two edges we have used consecutively. The same edge we have used consecutively. So that is a condition which I had to remove in the lemma statement. Okay, this is why the lemma premise is quite long. Conclusion is what you expect, that is cycle. How do you prove this? Yes. Yeah, let's check. I don't remember. Well, the path should have distinct vertices except the first and the last. Okay, so that is a path. Okay, so somewhere I have messed up. Where is that? So the length is also 2 vertices are distinct. Oh, length is, it's defined here, right? This is the number of edges. Yeah. Yeah, somehow I have to rule this out. I don't obviously want the edge to be repeated. Sorry? Yeah, maybe will it work if I say strictly greater? I want at least 3. That will rule out the edge repetition, right? Let's go with that. Sorry? Yeah. Length is the number of edges, which is in the first definition. x0 to x1 is 1 edge, and so on, so you have k edges. You are talking about this example, 1 to 1. In 1 to 1, there are only 2 edges. I mean the length is 2. Length is 2, so this is not a cycle, but a path. Is that clear? Bidirectional? No, so we are only talking about undirected graphs for now. We have not moved to directed. No, the edge set has both 1, 2 and 2, 1. That is how we defined very early on. I mean, anything else will not make sense. If you don't put 2, 1, then you are saying that it's a directed graph. You want both the adjacency matrix is symmetric. That's another thing for undirected graphs. Okay, so any question? So what do you do with the proof here? How do you show that there is a actual cycle? Sorry? Take the shortest walk, which becomes a path, and will that be enough? So in the path you have x0 equal to xk, and length you want at least 3, that is what we have added. If the length is 2, then the only way that can happen is that an edge was repeated. First edge was repeated. Is that fine? Yeah, so it's a one-line proof. So shortest walk P from x0 to xk. As we have shown in lemma 1, it's a path, and then if the length of the path is greater than or equal to 3, then we are done. If it is less than 3, then what can it be? It can't be 0 or 1. I mean, in particular, if it was 1, then you have a self loop, which we generally forbid. So the only possibility is that it will be 2. So what it means is that you have x0, x1, x2, which is the same as x0. Right? So you are using what was forbidden in the premise, x0, x1 edge both ways, which is a contradiction, which means that consecutive edge is same. Which is a contradiction. Okay, this contradiction means that this p less than 3 case is impossible. So p has to be at least 3, and hence it's a cycle, hence we are done. Is that clear? So it's a almost trivial proof, but way things work in graph is there may be many cases. Okay, you have to do this careful case study of boundary issues. But the main idea is just, again, the same thing, that take the shortest walk. In some sense, the shortest walk is already a cycle. If you ended where you started from, then the shortest walk is a cycle. Okay. So now we come to the definition of connectedness. or connectivity. So graph G is connected. What do you want here? Yes, so you don't want two cities which are unconnected, right? Contrapositive of that is that any two vertices you take, there should be a path. If for all u different from v vertices, there exists a path u to v. Okay, for any two distinct vertices, if there is a path, then you say that the graph is a connected graph. Otherwise, it is unconnected. So now you can, using connectedness, you can define relations between vertices. So two vertices are related if there is a path. So I'm using many short forms. I hope you can read the sentence nevertheless. So we'll say that UV are related if there is a way to reach V from U, and symmetrically in the case of undirected graph V to U. Now obviously there is a way to reach from U to U, right? This also we put in the relation. So this connectivity relation, is this an equivalence relation? It's reflexive, symmetric, and transitive, right? So this is the relation of connectivity. So the connectivity is an equivalence relation. And now there is a nice thing, because of equivalence relation, you will see classes of vertices. What is the physical interpretation of these classes in a graph? If U, V are in the same class, then they are connected, right? So these are called connected components of the graph. So this gives connected classes, which we will now call connected components of the graph. So if the graph is connected, how many connected components are there? Just one, right? Because everything is connected, so there is only one class. If the graph is unconnected, then you will have many, at least two connected components will be there. And maximum, how many components can there be? There can be n, in which case vertices are all isolated, no edges. So number of components is less than equal to the number of vertices and at least one. We are assuming at least one vertex is there. So components can be anything. So this is a very basic problem in computer science or in algorithms, that given a graph, you want to find these connected components, right? So maybe this semester you are doing a course where you do this DFS, BFS algorithm. That will give you the connected components. It's a very fast algorithm. It's a linear time algorithm. So that algorithm appears everywhere. It's a very useful trick. Okay, let's ask this question. Say from vertex 1, is connected to every vertex. What can you say about the graph? If the first vertex is connected to every vertex, then the graph, how many connected components are there? Oh, so you are saying that the graph is also connected. What is the proof? Yeah, so now you take, if you are talking about any u comma v pair other than 1, there is this central vertex 1, you can go from u to 1 and 1 to v. Right, so this you are using this undirectedness of the graph very strongly. Right, this will clearly not be possible in directed graphs. But in an undirected graph, if you find any vertex connected to everything, then everything is connected to everything. So then graph is connected. Okay. Right, so now let us see this at the level of adjacency matrix. So how does connectivity information appear in the matrix? Right? If you see a path pictorially between u to v, what does it mean in the matrix? Because matrix is only a collection of edges. So paths of length 1 you immediately see in the matrix. In that location of the array you will find a 1. How do you see paths of length 2 in the matrix? Is there a way? Because in your computer program you will only be given a matrix, nobody will draw a graph for you. Right? So now in the matrix, looking at the input matrix, how will you decide whether u to v there is a path of length 2? What will you do with the matrix? It's a programming question. Sorry? Okay. What are the steps? It's only an operator. What do you do with the matrix? Yeah, so to put it very simply, you square the matrix. It's a square matrix A, so you look at A times A. Okay, in A times A, now you will actually see in all the locations paths of length 2. Is that clear? So what about A square? This is the matrix product. So that is a great advantage about matrix representation, that you actually reduce questions of connectivity and many other things we will see to matrix analysis. So A square has the property that the u comma vth entry of A square is non-zero if and only if there exists a path from u to v. in the graph. Can you prove this? This just follows from the definition of matrix product. Okay, the matrix multiplication is actually defined exactly to achieve this. You can take this as a definition of matrix multiplication. Yes? U and V are isolated. U is equal to V. Yeah, if U is equal to V, then we have to do something else. Yeah, so I can say in this statement that U and V are different, or I can let me not say that, let me specify the conclusion a bit better. There exists a path U to V of length 2 in G. Okay, is that fine? So a path of length 2 means that U goes to W and W goes to V. So in the uth row of the matrix, so maybe we just write a line of the proof. So A square U comma V is what? It is the sum over all W's, A U W times A W V. Now the W which allows you to go from U to V will contribute a 1 here. Others will either contribute 0 or 1. But in any case, this will be positive. If and only if there exists U to W to V in the graph. Is that fine? Okay, so paths of length 1 is A, paths of length 2 is A square. But when you look at A square, you may see something other than 1, 0 and 1, right? You may see a 2 or a 3. What does that number mean? No, doesn't mean degree. A square's U comma Vth entry is a number. What does that number signify? It signifies how many W's there are, hence how many paths. So this then becomes even more interesting, that A square U comma V is exactly equal to the number of paths U to V of length 2. Right? So now actually this solves a very difficult question, because instead of finding all the paths from U to V and counting them, you can just do matrix powering A square, A cube and so on, and that will automatically count. So what is the lemma then for A to the K? A to the K UVth entry is number of paths of length K. In the graph. Right, so especially if K is equal to n by 2, where n is the number of vertices, then you can count how many n by 2 length paths are there from U to V, which otherwise would have been very difficult because there are exponentially many paths. Okay, so you can prove this formally as an exercise.